This section is entitled Building Functions from Functions. That is, we're going to take some functions and through various operations, we're going to get other functions. For example, first of all, let's do it by combining functions algebraically. That is, we're going to let f and g be functions with intersecting domains. And then for all values of x in the intersection, we're going to find their sum, their difference, their product, and their quotient. Okay. For example, let's let f of x be x squared and g of x be the square root of x plus 1. And we're going to find the formulas for each of these, the sum, the difference, the product, and the quotient, and the product of g and g. Okay, and then we're going to give the domain of each. Now, the domain of f is all real numbers, because x can be anything, right? However, the domain of g is not, because x plus 1 must be greater than or equal to negative 1. Right? Because we can't have non-negative, can't take square root of a negative number, right? So the domain of g is from negative 1 inclusive to positive infinity. Now, the intersection of these domains is the set of numbers that are in both the domain of f and the domain of g, okay? So they have to be in both, not either, that would be union, but intersection, which means both, all right? And so the domain of this must be the more restrictive domain, which in this case is the domain of g. All right. Now, to write that symbolically, that's the domain of all real numbers. Intersection, that's what that symbol means, with the domain of g. All right, and then that's going to be this. Okay, so that's kind of what we were saying up here in mathematical language. This symbol, the upside down U, means intersection. Right side up U is union, right? Upside down U is intersection. And whereas union can be either, this must be, these must be in both, all right? So that leads to the more restrictive domain. Okay, well, let's find their sum, and their sum will be this, simply adding the functions together. And the domain of this, of f plus g, is the same as the domain of g, right? Because we can't take square root of a negative number. So that leads to this domain. The difference, okay, gives us this function, which, and the domain of which is, once again, the more restrictive one, the domain of g, okay? All right, now their product will be this, and the domain, once again, because of we have this in there, the domain is from negative 1 inclusive to positive infinity. Their quotient, okay, well, this will be this. But now the domain has to be non-inclusive with negative 1, right? Because the radical sign is in the denominator, it can also not be 0. So x cannot be negative 1. So that leads to the open bracket here, the non-inclusive nature. Okay. And then finally, the domain of g times g, which will be root x plus 1 squared. Okay, now, as before, since we can't take the square root of a negative number, the domain is this, okay, the domain of g. Now, you might think, well, why don't we just simplify that to, you know, because square root of something squared is just itself, right? Yeah, but we got to be careful with that because x plus 1 has a domain of all real numbers. But that's incorrect for this situation because, once again, the domain of g is restricted to negative 1 inclusive to positive infinity. So we should leave it written as this, okay, because it's more descriptive. Writing it as x plus 1 would be would hide the restrictive domain nature. So we should leave it as this. Now let's talk about the composition of functions, which are functions within functions. By definition, the composition of f of g, composition f of g denoted by this symbology, is defined as this, okay, f of g of x. All right, and then the domain, you got to be careful with the domain again. The domain consists of all x values in the domain of g that map to values that are in the domain of f. Okay, so it has to be in both domains, once again. And writing it out in kind of pictures can be this. So x has to map to g of x, and the g of x has to be in the domain of f. All right. What do we mean by this? We'll see with further examples. Let f of x be e to the x and g of x equals square root of x. Find f of g of x and g of f of x and verify that they are not the same. All right, by definition, the symbology means f of g of x. G of x is the square root of x, so I'm going to plug that in for here, and we get e to the square root of x. G of f of x is this, okay? And f of x is e to the x, so then I'm going to plug that in for here, and I get square root of e to the x, okay? So we found those. Now let's verify that they are not the same. And to do that, I'm going to use, I'm just going to pick a value for x, and I'm going to let x equals 2. All right. You could let x equal 1, because that would be even simpler, right? But that's actually a little bit misleading, okay? Because of the identity properties of 1, stuff kind of gets lost in there. So pick something easy when you're doing this, but not 1 or 0, right? 0 would be actually lead to an incorrect answer. So let's let x equal 2, all right? So then f of g of 2. Okay, well, f of g of x is e to the square root of x, so that means that this is e to the square root of 2. And square root of 2 is 1.414. And then if you insert an e is 2.718, and on and on and on, but I'll just cut it off there. And then if you operate this into your calculator, you will find that this is equal to 4.11. All right, now let's take g of f of 2. G of f of x is the square root of e to the x. So that means that this is going to be e to the squared, e to the second power, which square root of something squared is just itself, and that is 2.718. And we can see that they are not the same. Okay, so it's verified, right? There's even another reason that they are not the same, and that's because the domains are not the same. The domain of f of g of x, okay, is x is greater than or equal to 0, because anything under the radical sign can't be 0, or sorry, can't be negative, so x could be 0 or greater than 0, right? Whereas in this case, for g of f of x, x can be anything. If it's negative, that just means you have 1 over e to some power, which is still a number to some power, and it's a positive number to some power. So you can take the square root of that. So the domain of g of f of x is all real numbers, while the domain of f of g of x is restricted. Okay, so that's another reason. All right, let's do this example. Given these functions, let's find the domains of these. So f of g of x, okay, is going to be plug in that for the x here, and we get that, and that leads to something. But to be in the domain of f of x, remember, x must be first in the domain of g of x, and g of x is restricted to numbers greater than or equal to 0. So because of that, the domain of this f of g of x must be that restricted domain 0 to positive infinity. Okay. Now you could simplify that to, square root of x squared. You could get that x minus 1, but the domain of that is all real numbers. So that's a little bit misleading. So it's better to leave it written as this to denote the restricted domain of g. All right. Now let's do g of f of x. Since f of x is x squared minus 1, I can just plug it in there, and we get this. Okay. Now, the domain of f of x is all real numbers, right? Because x can be anything. But when we take the square root of that, it has to be non-negative. Okay. So the domain of this is restricted to numbers for which x squared minus 1 is greater than or equal to 0. Because you can't take square root of a negative number. And that will lead to this domain. Okay, now we're going to decompose functions. So to decompose functions, we're going to let h of x be this, and then we're going to find other functions such that this h of x is f of g of x. Okay, and with a little experience and a little experimenting, you'll come up with this. Let's let g of x be x cubed plus 4 and f of x be root x. So when I take the f of g of x, since f of x is just x under a radical sign, and I can take this x cubed plus 4, put it under the radical sign, and I get this, okay, which indeed is h of x. Okay, let's do another example. Let's let h of x be this. And once again, we're going to find functions such that h of x is equal to f of g of x. All right, pause this video and see if you can come up with an answer to that, and then come back. Okay, here's what I got. Let's let g of x be x squared plus 1, and f of x be 2 over x. So that when I have f of g of x, that's going to be f of x squared plus 1, and x squared plus 1, just plugging that in for x, we get this, which once again is the same as h of x. All right, as a final example, we're given a graph, and we want to find various things. For example, we want to find f plus g of 2, okay? Now, f plus g of 2 is really f of 2 plus g of 2. Okay, now from the graph, f of 2 is 0, g of 2 is negative 1. And that leads to an answer of negative 1. Let's do this one. F times g of 1. This one's going to be f of 1 times g of 1. And let's see, what's f of 1? F of 1 is 3. G of 1 is negative 1. And that multiplies to negative 3. Finally, let's do f of g of 2. F of g of 2. Well, what's g of 2? G of 2 is negative 1. So that means we want f of negative 1. And f of negative 1 has a value of positive 3. So that's how we do that. So using a graph, you can break these up or take the composition, and using the graph, we can come up with some answers. Okay, time to do some practice problems.